Thank you, indeed. I am Alex. I'm a PhD student at Stanford, and I actually work on both cryptography and formal methods. And one of the things I'm excited about today is that I'm going to get to tell you about both of those areas. So we'll be talking about CirC, which is a compiler infrastructure that aims to support both crypto systems and formal verification. So let's start by talking about why crypto systems need a compiler infrastructure in the first place. The reason is that essentially most modern crypto systems are computers. Consider, for example, multi-party computation. The classic problem in this space is that there are two different entities, each of them has an amount of money, and they want to know whose amount is bigger, without revealing their amount to the other party. Modern MPC protocols can solve this problem, but they can actually do a lot more. In fact, they can evaluate any user-defined function f over secret data distributed among multiple parties, so long as the user writes down f in an appropriate computational representation. Since this system is user programmable, I would say it's a computer. And it's not the only crypto system like that. Indeed, fully homomorphic encryption applies user-defined functions to encrypted data, and zero-knowledge proofs allow one to show that a user-defined function would output 1 on some secret data. So since there are so many different crypto systems that are user programmable, it's unsurprising that there are a number of compilers that translate from various high-level languages to the representations needed by different kinds of crypto systems. I have a bunch of those compilers on the slide, and all of them are good projects that I respect, but they also all fall short one way or another. Broadly speaking, the academic projects are often incomplete or buggy, which makes them hard to use, and the industrial projects in orange are more reliable, but they achieve that reliability by supporting very bare bones high-level languages. For example, Socrates, one of the languages that we'll discuss later, doesn't even allow the programmer to write if statements. And so a natural question is why are compilers in this space falling short? In fact, in our view, the reason for that is essentially that this compilation problem is hard, and all of these compilers are trying to solve it on their own. And so a second natural question is whether or not it's possible for them to share infrastructure. Can we build some kind of LLVM-style compiler infrastructure that can be shared among different compilers in this space? And our proposed answer is yes. So I'll be telling you about CirC, which is our interpretation of that infrastructure. First, we'll talk about CirC's design and computational model. So by the end of the talk, you should understand what kinds of compilation CirC does and does not aim to support. Then we'll talk about CirC's performance, more specifically the performance of outputs produced by compilers built using CirC. And finally, we'll talk about another way in which CirC can be useful, namely its potential to enable crossover opportunities, situations in which multiple CirC targets can be combined in the service of some high-level application. That probably sounds kind of weird right now, but we'll make it more concrete at the end of the talk. So this is our agenda, but truth in advertising, I need to say that while CirC's vision is broad, this paper and the talk today focus on just a subset of possible CirC targets. We'll be talking about zero-knowledge proofs, SMT logical formula, and constrained optimization problems. Multi-party computation, fully homomorphic encryption, those are ongoing and future work. Okay, so let's get into it. CirC's design and computational model. To understand how CirC is designed, we have to understand, in some sense, what it's trying to do. So let's talk about what it needs to produce. To first order, you should imagine that these different kinds of crypto systems, zero-knowledge proofs, etc., expect the computation to be represented as an arithmetic circuit. So what CirC is trying to do is produce some kind of directed acyclic graph where the inputs come in from the left and are connected by wires to gates that perform some operation in a finite field, like the integers mod p. Different backends might support custom operations. You might imagine that zero-knowledge proofs will sometimes support equality assertions. And different backends will have different concrete cost models, but to first order, every backend is happier if the circuit is smaller. And so CirC's goal is to take some high-level input computation and translate it into an arithmetic circuit that is equivalent and has minimal size. And this is actually a pretty challenging task because high-level languages, including this small snippet of pseudocode on the left, have a number of features like mutable variables, if statements, for loops, and more that don't have natural analogs in a circuit. And so in this compilation pipeline, a lot of transformations have to be applied. Variable mutation has to be eliminated, perhaps putting the program into some kind of SSA form. Branches have to be eliminated. All paths need to be explored with side effects appropriately guarded. Loops, those don't exist in a circuit, so we'll have to unroll them up to a bound that comes from an analysis or perhaps from the programmer. And the list just goes on. There are a whole host of transformations that need to be applied, and noting their complexity and how numerous they are, you can see why compilers in this space have a hard time. This is harder than compiling C to assembly. But when my collaborators and I, when we looked at this list, we saw cause for hope, because these transformations are exactly the transformations performed by something called a bounded model checker. For those of you who aren't familiar, bounded model checking is a formal verification technique where you take a program and a query about it, perhaps you want to know if there's a use after free, and you translate these objects into a logical formula, like an SMT formula, whose satisfiability is equivalent to the answer to the query. By solving the formula, you can then get an answer to your query. And this pipeline is the subject of decades of research, but I just want to focus on one part of it. That white box in the center that combines the program and the query into the formula, what do we call that? Folks in this space call it a bounded model checker, but I would call it a compiler, because its inputs are computations, and its output, a logical formula, that's another kind of computation. And looking at logical formulas as computations is useful for us because they share some features with arithmetic circuits and the kinds of computations that we're interested in. So namely, all of these different kinds of computations, logical formulas, arithmetic circuits for zero-knowledge proofs, etc., they're all mutation-free, control flow-free, and of fixed size. They take a certain number of inputs. If you want to handle more inputs, you need a bigger circuit. And so these three features, they define the circuit model of computation. So we're looking for a compiler to circuits. But we're not just looking for a compiler to any circuit, because there's another common thread, which is the fact that all of these domains have variables of restricted knowledge. And what that means depends a bit on the particular domain. In the case of zero-knowledge proofs, there is some secret data that only the prover knows. The verifier doesn't know it. And in the case of logical formulas, there are variables that are existentially quantified. We don't know if values for those variables exist. And we're hoping that the SMT solver or the SAT solver will figure that out for us. And so broadly speaking, we refer to these kinds of knowledge restrictions as existential quantification, perhaps with some metadata attached that indicates who knows the value or who is responsible for finding it. And so we identify as our key computational abstraction the existentially quantified circuit. That's what we're trying to compile to. And like I said, we're trying to compile from some high-level language that might include mutation, control flow, variable size data, etc. And so this is a hard compilation problem to solve, but the architecture that we use is, at least in my view, more or less what you'd expect. There's an intermediate representation, CirC IR, which is a circuit IR, but it's a circuit IR with a very rich type system. So it has a whole bunch of different kinds of primitives, as well as fixed size arrays and tuples. The first stage in the compiler involves running a front-end extension that translates from some high-level language into CirC IR. Then we take that IR and we transform it. We optimize it, we eliminate complex constructs like the tuples, and then we take the simplified IR and we give it to a backend that lowers to the particular EQC that some target expects. So that's the architecture at a high level, but when you look at the two halves of it, the front ends and the back ends, they're not equally difficult to build. The back ends are translating from one kind of circuit, RIR, to another kind of circuit. So in some sense, they're just remapping types. This isn't so hard to do, but what the front ends are doing is far harder because they're mapping a high-level program that might have stateful semantics, mutable variables, etc., into a circuit, which, as we discussed before, is kind of complicated. And so to assist in the construction of front ends, CirC provides a library called CirCify, which is essentially a library for representing stateful semantics inside of circuits. It exposes an API for interacting with variables, interacting with control flow, interacting with function calls, interacting with stack arrays. And when you use that API to, for example, write a variable or read a variable, CirCify automatically generates chunks of CirC IR that encode the stateful semantics of the operation that you just did in the state-free circuit IR. So CirCify is a pretty clever piece of machinery. That's definitely where the brains of the operation is. But it ends up working, and it makes writing front ends very easy because you basically just sort of write an interpreter for the high-level language that you're trying to compile. But whenever your interpreter would interact with its environment, you don't interact with your environment, you interact with CirCify, and it sort of automatically embeds your environment into the circuit. At least that's how I think of it when I write these frontends. So this is how CirC works at a high level, but now let's talk about how well CirC works, what you can do with it. We did a whole bunch of stuff in the paper. I'll just tell you about one case study. We built a compiler from this language Socrates to zero-knowledge proofs. You're probably not familiar with Socrates, but it's this language from the blockchain community that was designed expressly to be compiled to zero-knowledge proofs. It's a pretty reasonable language, and funding for it is ongoing. There are people still working on it. Given the amount of investment, it's unsurprising that the compiler itself is a pretty substantial piece of software. The core of the compiler, the optimizer, on its own is 28,000 lines of code and was developed over quite a while by a whole host of individuals. On the whole, this is a good compiler, and so our goal was essentially to replicate the Socrates reference compiler by building on CirC. We hoped that we would be able to do that more easily than building the compiler from scratch, because we would be benefiting from the common infrastructure. And I think it's safe to say that the case study exceeded even our expectations. So we were ultimately able to replicate the functionality of the Socrates compiler in a mere 700 lines of code in 1 week. And despite the fact that there was a huge reduction in the amount of engineering effort that went into our Socrates compiler, it actually produces output that's slightly better than the original. At least that's what we found on average when we compiled every program in the Socrates standard library. So why did this go so well? It's not because we're smarter. It's because we weren't building a whole compiler from scratch. We were building on CirC, an existing infrastructure. So all we really did was write a front end to that infrastructure, and then the infrastructure took care of the rest. And so this is a good example of how compiler infrastructure makes it easy to build very performant compilers. But CirC has other benefits as well, and the kind of benefit I want to discuss now is what we call a crossover opportunity. And so the observation here is that CirC's different targets, they're not ARM and x86. They actually serve very different purposes. We've got a ZKP target that can give you private efficient proofs. We've also got an SMT target that can answer satisfiability queries. We've got an optimization target that I haven't mentioned before, but can solve constrained optimization problems, and even things like multiparty computation and FHE, they seem like they're in scope too. And so the question is whether or not there are some applications that would want to compile to multiple targets in order to solve some problem. And of course, the answer to that question is yes. The only limit here is our creativity. So I'll tell you about one crossover application that we explored, which is using the SMT solver to optimize a different compilation pipeline. There are many ways that you might imagine doing that. We explored one instantiation, which is using the SMT solver to figure out how many times to unroll a loop. As I said earlier, when you're compiling to circuits, there are no loops in circuits, so you have to unroll the loops. How many times do you unroll? Well, if you unroll too many times, then you're just generating a bigger circuit, which is a waste. And if you unroll too few times, then you can't model some executions of the program, which is even worse. And so the question here is, how do you find the Goldilocks number? And it turns out you can use an SMT solver to do that. Essentially, you do that by doing incremental compilation. So you take your program, you start compiling it, you encounter some loop, you unroll it once, and then you ask the SMT solver whether there are some inputs to the program that would cause the loop to run at least one time. And if the SMT solver says, yes, this path is still feasible, you keep going. And you unroll and unroll and unroll. And let's say after the 33rd unrolling, the solver finally comes back to you and says, no, there are no inputs that will cause this loop to run 33 times. At this point, you can throw out the 33rd compilation result, take the 32nd, exit the loop, finish compiling, and ultimately lower to whatever backend you actually cared about in the first place. That might be a zero-knowledge proof. That might even be producing an SMT formula that encodes a more complex query about the program that you're compiling than how many times this loop runs. But the point is, whatever you're doing it with better CirCIR, so that the backend is probably going to perform better. Now, in theory, any compiler can do this kind of SMT-assisted optimization. The only problem is, of course, getting the SMT solver to understand the compiler's IR. And the cool thing about CirC is that we get that for free, because SMT is one of our backends. And so rigging up this pipeline in our C front end took a mere 18 lines of code, which is actually sort of a lot of fun. Okay, so this is one of the crossover applications we explored. I also told you about one of the case studies. Of course, there's a lot more in the paper. We build other backends. I mentioned this optimization backend based on integer linear programs. We build other front ends for a subset of C, for a dialect of Datalog, for a hardware description language called CirCom. We also explore other crossover applications. We use the SMT solver to lint one of our languages. We explore automatic zero-knowledge proofs of exploitability and show that we can trigger an old CVE in OpenSSL in zero knowledge. And sort of the list goes on. Of course, this is a compiler paper, so we benchmark, and benchmark some more. We benchmark our compilers against other people's compilers. We benchmark our compilers against hand-tuned code. We even do benchmarks in which we verify that our optimizations are benefiting multiple different backends. So we're sort of verifying that the common optimizations are actually common, which is just sort of a good reality check. And yeah, so that's more or less what you'll find in the paper. But there's also a lot of ongoing work that I want to tell you about. We've been, of course, investigating other extensions to the compiler. We've been developing a language called Z#, an extension of Socrates, with some partners in industry who have a commercial application in mind. One of the cool things about Z# is that its type system is rich enough that we actually need an inference engine. And the way that we do inference, rather than writing our own solver, is that we kick it out to the SMT solver and have that do the inference for us, which is kind of cute. We've also been working on backends with folks from Carnegie Mellon for the other crypto systems that I alluded to earlier, and we've been using those as a platform to do other kinds of research into how you compile effectively for those backends. And there are also other folks, not us, who have been using CirC as a platform for other kinds of compilation research. So later this year at Usenix Security, there will be a paper by some folks at University of Pennsylvania, including Sebastian Angel, who's in the audience right now, on how to compile numerical optimization problems to snarks, which is in some sense totally orthogonal to CirC, but by building on CirC, they were able to get to the research faster than if they had to build the compiler themselves. And we think that really CirC would be a good platform for investigating other kinds of compilation problems as well. So basically, we're at the end of the talk here. I've been telling you about CirC. This is our common compiler infrastructure for translating high-level programs into existentially quantified circuits, such as those used by crypto systems. The key idea here is that existentially quantified circuit. We found that CirC makes it easy to build compilers that perform well, because those compilers benefit from shared optimizations. And we think that ultimately, of course, the most exciting thing is whatever happens next. We're very interested in new front ends, new back ends, and I cannot emphasize this enough. If you have bumped into some problem that looks like a compilation problem in this place, please come talk to us. We'd love to hear about your problem and help you figure out whether or not CirC would be a good tool for working on it. Thank you very much. I'd be honored to take any questions.
Yeah, great. Thanks for the wonderful talk. Yeah, wonderful work and wonderful talk. If you have any question, please use the microphone to ask questions.
Hi, this is Gary Tan from Penn State. So I suppose your C subset does not model the heap, right? No memory allocation, that kind of things. If you want to extend your infrastructure to handle that, how hard would that be?
Yeah, so yes, we don't support dynamic allocation on the heap in our C subset. We only handle stack arrays. And we think that that's a hard compilation, like a hard research question. The heap is just a lot more challenging to reason about.
Okay, thank you.
John Saracino, Cornell. Have you thought about verifying the correctness of CirC?
Yeah, certainly. We're very interested in that. I mean, in sort of to first order, this is a problem that's quite similar to translation validation or compiler verification in general, and a lot of the existing techniques should apply very effectively. There is one sort of quirk, which is that we are very interested in these arithmetic circuit backends, which are defined over finite fields, that existing tools are pretty bad at reasoning about. So SMT solvers are basically hopeless on this. We don't think it has to be that way. We think that with slightly better solver technology, we could make a lot of progress on that, and that's something that I'm actively working on right now and very interested in exploring more.
Cool, thanks.
Hey, great talk. I'm Andreas Kogler from Graz University, and I wanted to ask, would it be imaginable to use basically LLVM IR as input for your front, also to basically fuse those two?
Like the previous questions, this is a great question. And so the relationship to LLVM is something that we've thought very carefully about. It certainly is possible. You could imagine trying to sort of translate LLVM IR to CirC IR, but we think this is quite challenging. And the reason is that LLVM is really intrinsically designed to be to compile programs destined for RAM register machines, which are like very different from circuits. In some sense, like LLVM's IR is sending the design in the wrong direction, and the optimizations are optimizing in the wrong direction, and that's why we decided to sort of go our own way. But you could imagine making a bridge that's just very inefficient.
Yeah, okay. I see.
All right,
Thank
great.
you.
Wonderful. I think given the time limit, we need to move on to the next paper. So if you have additional questions, please go out offline.